Hi, and welcome to Codex. Our speaker today is Markus Grassl, who is a senior scientist at the International Center for Theory of Quantum Technologies at the University of Gdańsk. Dr. Grassl works in quantum information and quantum error correcting codes and has been a world leader in the computer search for SIC-POVMs. Today, he will tell us about computing SIC-POVMs using permutation symmetries and Stark units. Take it away, Markus.
Thank you for the introduction, and thanks to all of you for the invitation to give me the chance to present our work. It kept me busy for almost 3 years now, kind of having more and more new ideas and new insight, and it's time to get the results out. And unfortunately, we don't have yet our publication, or at least the preprint, available, but you get the chance to see the slides also after the talk, and hopefully also soon our paper. So I don't think I have to tell the audience much about Zauner's conjecture and what it means to us, but nonetheless, to be on the same page, I will give a bit of introduction to that. And then first, I will report how we found all the numerical solutions. That is mainly joint work by Andrew Scott, and Andrew Scott provided all kind of the basic programs for that. Then one of the key steps for me was when we discovered how more symmetries can help us to push the limits further, and I will briefly discuss what the symmetries look like, in particular also a paper of the same name, relation to Fibonacci-Lucas numbers. And then kind of we are switching gears and start with our numerical solutions and try to get exact ones from them. There is essentially two methods. The one is based on overlaps. That is kind of works by others. And then what I discovered was that we can use permutation symmetries and get much further than that. And then taking those solutions, actually in the end, we found that we can take Stark units. I will briefly tell you what they are in the talk and get directly to compute solutions. I will give you a bit of an outlook, and already now I give you the spoiler. We still have no proof for the existence of SIC-POVMs from infinite sequence of dimension, but I hope that this talk and our work will give you a bit more of an idea how we could achieve that goal. So the problem, as you all know, is very simple to state. The question is to find d-squared unit vectors such that in the complex d-dimensional space, such that their overlap modulus squared is equal to a constant, and the constant turns out to be 1 over d plus 1. And so just also to put it in the framework of the community here, what we have is that those vectors form an equiangular tight frame. That's also the condition for POVMs, or a finite unit norm tight frame. And the first idea one can have is just to write down the corresponding equation. So we write down the vectors, splitting them into real and imaginary part in order to be able to express this inner product here in terms as a polynomial function. And what we have for our d-squared vectors, we get 2 times d cubed variables. We get d-squared equations from the normalization condition, and we get d-squared choose 2 equations for all the pairs of vectors that have the inner product. That quickly becomes infeasible. Actually, already for dimension 3, we are getting in some trouble when we try to do that. Also related to the fact that we have a lot of symmetry and we should make use of the symmetries. And one way of making use of the symmetry is actually imposing symmetries. And that is via the Weyl-Heisenberg group, where we have a shift operator and a phase operator, also known kind of as translation and modulation operators. And that at the end of the day gives rise to a specific ansatz that we take just an orbit under the Weyl-Heisenberg group. So we just take a single vector and compute the full orbit of that. And in frame theory, what we would have is a finite Galois frame, since we're just taking one kind of so-called fiducial vector, and then we apply modulation and translation to it in finite space. So we are computing effectively on the torus of d squared. Again, we can parameterize our vector. We can now also make use of the fact that we have a phase degree of freedom. So we can pick the first variable to be real. So setting the imaginary part to 0, then we get only 2d minus 1, so a linear number of variables instead of a cubic number 1. But nonetheless, when we try to solve these polynomial equations already for, say, dimension 6, 7, we have to be patient. And of course, with nowadays computers, it's a bit more easy. But when Zauner made Conjecture in 1999, he actually did calculations mainly by hand. Also what Markus Appleby did for many of the small dimensions. I'm more the computer person, so I always give it to the computer. So one idea kind of to cut the problem further down is to impose even more symmetries, and those symmetries are now mainly known as the Clifford group, but also in the mathematics literature known as the Jacobi group. And those are essentially all the matrices that normalize the Weyl-Heisenberg group. And it turns out that those matrices can be represented just by 2x2 matrices with determinant 1. There's another automorphism which cannot realize by linear operation, and that is the operation corresponding to complex conjugation in the defining basis of our Weyl-Heisenberg group's representation. And that changes the phase operator to its inverse. And in terms of matrices, we get this diagonal matrix with 1 minus 1. Is that just corresponding to complex conjugation in this particular basis? So we can impose more symmetries, and by that reducing our parameter space and get more solutions. And effectively, what Zauner stated in his PhD thesis back in 1999, and he didn't make it a prominent conjecture, it was more in the main text where he made that kind of as a paragraph saying what we have seen so far makes it plausible for the following, and the following phrased in our terms now is that in all dimensions, we would have a SIC-POVM, which is the orbit of a Weyl-Heisenberg, a rank 1 operator. And also he gives a particular symmetry element, which I label S here, which has order 3. And also this element has the nice property that essentially it cuts the d-dimensional space into 3 essentially equal parts. So that reduces the dimension to 1/3. And the conjecture by now is supported by numerical solutions for all the dimensions up to 193, plus some additional ones. And we have exact algebraic solutions for a lot of dimensions, but still we don't have a proof even for some quite sporadic but infinite sequence of dimensions. If you were able to solve that, as we already heard last week, if you post a paper this year, you would earn 2021 euro, increasing by €1 every year. And you can find that in this archive paper. So how can we do numerical search? And that was our workhorse for a long time, and to some extent still is. What we do is actually, some people call it the second frame potential, but we can just look at the frame potential in terms of a tool design. What we do is we tensor each vector with itself and compute the corresponding frame potential for that one. So that gives the fourth power, since clearly when we calculate the inner products, we get just the square. And also we make the additional ansatz that our vectors are the orbit under the Weyl-Heisenberg group. And then we can just express that as a function in terms of our fiducial vector. And it turns out that we can actually remove the phase or modulation operator and the shift operator and get an alternative expression where all these matrices are gone. And the expression is written down here. We get a sum, which is kind of over monomials of degree 4. Then we take the modulus squared and we sum over all indices j and k. And it turns out those expressions are the very same. And by the Welsh bound, we know that this quantity is lower bounded by 2 over d plus 1. And whenever we reach equality in this bound, we know that we have an equiangular set of lines, and therefore we have a fiducial vector for our Weyl-Heisenberg SIC-POVM. And the main idea is now just to minimize this function, but kind of the caveat is that we have to constrain our vector, of course, to be of unit norm. So when we rephrase that, it turns out that's the main idea introduced by Andrew Scott, that instead of minimizing everything over the sphere of unit vectors, we just take an arbitrary function, or say an arbitrary vector, but evaluate our original function by the normalized vector. So divide formally by the norm of the vector. And also, in order to prescribe the symmetry, we can introduce an arbitrary projection operator and introduce that also in our function. And then if you do kind of first year, second year calculus, applying the chain rule to calculate the gradient of that, it turns out that one can express the gradient just in terms of the original function. Excuse me. So by that, despite the fact that we are starting with a function which itself has qubit complexity, and we have to compute a gradient, that means a vector of d many derivatives of that function, we can store intermediate values and have an overall complexity which is only cubic instead of quartic to calculate that function. So there is an efficient implementation of that function together with all these projection operators written in C++ by Andrew Scott, which then later I added some parallelization and also tried to use some GPU additionally. And all of that is based, that was also already introduced by Andrew, by a particular minimization algorithm, which uses both the function and the gradient. And kind of the problem with that is that when we search for the global minimum, which we know, if we achieve that, we have a solution. Almost all the time we run into local minima, and we don't have any good heuristic to choose initial points. It's also the problem kind of to do some kind of sampling to see which are regions of attraction or whatever. So we just boldly pick a random initial point, run many, many instances in parallel on the clusters by the Max Planck Society and also another computer science kind of a provider to the Max Planck Society in Göttingen. And when we look at how many trials we have, we are getting in the order of kind of 10 to even 100 million trials of initial points just to find one global minimum. And that accumulates for the kind of the largest dimension. We have a solution for, we have 13 CPU years just to find a single solution in 193 dimensions. There was also the attempt to go for dimension 5779. Why that dimension? We will see later a little bit. But since we have a complexity that is cubic in the dimension, we could only run something like 55,000 trials in a bit more than 17 years of GPU time, now using my kind of naive implementation to make use of the graphical processing unit, but we were not lucky to find any solution. And why that was the case is kind of for small dimensions, we can get a bit of statistics. If we just run the minimization for random points and see how many initial points do we need in order to get 100 solutions, then it turns out we have an exponential kind of growth of the number of trials we need, since here we are plotting the dimension with linear scale and the number of iterations in logarithmic scale. When we impose the Zauner symmetry, we can lower kind of the base instead of 1.22 roughly to 1.09. But again, we have an exponential kind of running time scaling with dimension. I did this exploration that up to 95 with Zauner symmetry and up to 60 without. When we take a slightly closer look at that, now only detection starting at 50, now we have a linear scale for the number of iterations. And it turns out we get a very high maximal number, but we might also be lucky and find a solution very quickly after just a few iterations. So again, the problem is that we don't know whether we are lucky or whether we are unlucky. We just have to keep our fingers crossed, and that is what I tried to do for 5779, but I failed. So the question is, can we get more help by symmetries? So what symmetries can we expect? What Andrew did was taking kind of small order symmetries of order 6, for example, and he found a solution in dimension 124 with his method. I was at the same time working on symmetry analysis programs, and it turned out that his solution, despite having only prescribed symmetry of order 60, actually has a symmetry group of order 30. So we can have more symmetry, and using more symmetry cuts down the search space to some smaller dimensional space, and we have a better chance to get a solution. So we
Sorry,
found,
Markus, what is the difference between you say symmetry group of order 30, the prescribed order 6? What is the distinction then between the order and the prescribed order?
So the described order, that was the kind of projection operator we had in our gradient function. And we are just projecting onto an eigenspace of an order 6 symmetry. So that was kind of what was prescribed symmetry. But then the solution that was found turned out to have a higher symmetry. Clearly,
Gotcha.
one could have tried to impose a bigger symmetry in first place. But in particular, at the time when that was found, it was unclear what are the potential symmetries. And looking at the small dimensions, kind of Andrew identified some symmetries which might exist in a sequence of dimension, but he fixed the order of the symmetry and let the dimension go. And now kind of that was kind of for me, a kind of essential key point, that we now have a symmetry where the symmetry group orders with 6k, and k is actually positioned in that sequence. And using that additional symmetries, we were able to turn also this numerical solution into an exact one. We also found one for dimension 323, and also for the next 2 dimensions, with the help of the prescribed symmetry, the numerical algorithms allowed us to find a numerical solution. Also, yet another unpublished kind of paper is there is a kind of more or less straightforward generalization where we replace the Fibonacci and Lucas numbers by their generalization. instead of the matrix given here, which corresponds to the recurrence relation for Fibonacci numbers, we are replacing just this lower diagonal entry with an integer number m, and we get to generalized Fibonacci numbers. When we look kind of how much symmetry we get for the dimensions, we look at this plot. Now we have a logarithmic plot for the dimension and a linear scale for the additional symmetry. And the sequence I showed you before, corresponding to Fibonacci-Lucas SIC-POVMs, that turns out the sequence of symmetries where the order grows the fastest with the dimension. But since we have kind of exponential scale, we have logarithmic scale for the dimension, linear scale for the symmetry. That means the symmetry only grows with the logarithm of the dimension. And we conjecture that this is actually the most help you can get by the symmetry. So when we go to dimension 5779, we would have a symmetry of order 54, cutting it down to something like a bit more than 100 dimensions. So it might kind of be in reach, and that was one of the reasons why I gave this dimension a trial. We already had the 2208. But now when we look at the known solutions, those are essentially all these blue spikes, again with logarithmic scale for the dimension, linear scale for the symmetry. What I've plotted here in addition is the ratio of the dimension by some constant 50, 60, and 70, or turned the other way around. If you divide the dimension by the order of the symmetry, if you are kind of on the left-hand side of this green curve, you have a ratio of 50. With the orange one, you get 60. With the yellow one, you get 70. And that appears to be roughly the bound which we are hitting when doing just our naive gradient descent, for which we are just picking random initial points and doing gradient minimization. The 1299 is already a little bit outside of that, and we do have just a few solutions out there, but it might be possible, again, if we are lucky, to get dimension 194. 195 actually is already done. So we might push the limits a bit further, but to me, it's not really justified just for the mere kind of a number crunching to push this limit of 193 any further. So we need more structure, and more structure is actually found by connections to number theory, which you have already heard in talks in the seminar series by Markus Appelby, Steve Lamia, Jean Kopp. Jean will have another talk in December, and there you might get more information about the number theoretical conjecture. But the point was, by inspection of the exact solutions, Andrew had published in our 2010 paper for the largest dimension back then being 48. It turned out that the field in which the solutions live all have a very nice structure, and that led to what I sloppily call the Weyl class field conjecture, saying we are starting with a quadratic field over the rationals. They're taking the square root of a positive number, which is the square field part of d plus 1 times d minus 3, d being the dimension we are in. And then we have a tower of other fields. And it turns out that this biggest field is a Weyl class field, which we are, at least in principle, able to compute and know kind of what this field looks like, what the Galois group over the quadratic field looks like. It's actually an abelian group, so it's the nicest you can look for. And what is even more, so just repeating the sequence of towers, if you go to these papers, you find some statements which are stated as facts, as observations the authors had made. And it turns out that this fact 8 says the Galois group of this intermediate field over this field E0, which turns out to be the Hilbert class field, acts as a permutation on the overlaps you're computing. And slightly more precise, it's if you apply an automorphism to this inner product, clearly now as a kind of not taking the absolute value squared, since the absolute value squared should be a constant. So this still contains all the information we need. It's essentially part of the Gramian matrix of our set of lines. Then this equals the overlap for another kind of operator, and these displacement operators I put in the footnote are essentially powers of A and B with a suitable phase factor that makes all that nicely to happen. Moreover, the matrix G, which acts on this exponent vector AB, that is a matrix which commutes with the matrix that encodes our symmetry. Unfortunately, we don't have the explicit correspondence between that, but just by this fact, one can make use of it, the action of the Galois group. And that was done in this paper, which Dustin, he had this blog post that Zauner's conjecture is true in dimension 17. And that was actually related to Tianjin's PhD thesis, where he applied these techniques to dimension 17. The essential observation is that when we look at these expansion coefficients of the projection operator, equivalently the overlaps, then they form an orbit under Galois operation. And therefore, when we calculate the orbit of the overlaps with respect to the matrix group corresponding to the matrices here, then we get a polynomial which is invariant under the Galois action. And since it's invariant under the Galois action, the coefficients of this polynomial lie in the number field of small degree. In the minimal case, this field would be actually the Hilbert class field, or we might even go down when we take the full group to this quadratic field. So when we have a solution to sufficient high precision, we can calculate numerically this polynomial by just kind of computing the polynomial which has the numerical values as its roots. And then we can apply integer relation algorithms to get the potentially correct algebraic numbers. If our precision was sufficiently high, we get the correct numbers. Of course, all provided that the underlying conjectures are true. When we have this polynomial, then we know that the polynomial would factor over the Weyl class field. So we need kind of to get expressions for that. If the degree of the field is not too big and the structure is kind of nice, the computer algebra system Magma is able to calculate generators for us. So we can compute the roots of that, and then we can take the roots of that and we can reconstruct our projection operator from these expansion coefficients. So what they had in their paper was they expanded the list of solutions up to dimension 48. Of course, not all of them, but just for particular ones where the fields were nice. Also, they extended the procedure to non-minimal fields. So there were more solutions we had which do not obey the full Weyl class field conjecture, but this kind of property that we have coefficients which form orbits under the Galois group, that still holds. And what already Steve Lamia in his talk kind of highlighted or advertised was that the method can be expanded to dimension 100 in particular, and maybe Gene will give us more of the details in his talk in December. But what I want to stress is, if we directly apply this method, we have d-squared expansion coefficients we have to solve for. And so dimension 100 already means we would have 10,000 expansion coefficients to solve for. There is the symmetry addition that cuts the number of different elements down. Also, when the field is kind of nice, the degree of these polynomials is not 10,000, but nonetheless, it's already quite some challenging calculations. So one additional idea is to look at what is this matrix. They were in first place just matrices 2 by 2 invertible. But if they have determinant 1, then those matrices correspond to unitary operations in the Clifford group. So we have unitary matrices, and just to get rid of one of the indices, I call it T sigma. And we have the following situation that when we apply our Galois automorphism to this overlap, then by the Weyl class field conjecture, this implies a transformation on the indices of this displacement operator. But then the correspondence between those matrices and this representation as symmetries of the Weyl-Heisenberg group, it turns out that we are conjugating this matrix, the displacement matrix by T. So I'm using here the physics notation for the inverse. And then by the cyclicality of the trace, I can move this around and have the operation on the projection operator instead of the displacement operator. So from this equation, it indicates that we get an action of the matrix, now actually the inverse of it, on the projection operator and also on the state. Moreover, it turns out when we just look at diagonal matrices with determinant 1, then already in Markus Appleby's paper of 2005, it turns out that the matrix here is just a permutation matrix. So we have some permutation acting on our fiducial vector, but still it's only inside of the trace. So for the moment, just make a bold assumption and say that applying the Galois automorphism to our Weyl-Heisenberg element, the displacement operator, leaves it invariant. So that essentially means that we have a Galois automorphism that fixes the cyclotomic field. If that is true, then we can remove the trace out of that and indeed have an action of our automorphism on the projection operator that corresponds just to a conjugation of this operator. Since we have assumed that this is just a permutation matrix, it turns out when we apply our automorphism to a matrix element, we are just multiplying the indices by this element alpha. And clearly kind of the calculation of the indices is modulo D, so we are numbering them from 0 on. So just as a reminder, it's a bold assumption we are making here, starting from this conjecture, but that gives us a permutation action on our projection operator. When we look in particular at the first column of our vector, we find that clearly the 0 is a fixed point of our permutation action. So what we get is a permutation on the indices of the first column of our. So we can take this as a fiducial vector However, it turns out it might happen that the first column of our projection operator is actually 0. So that was observed for these particular dimensions. And in that case, we cannot use the first column as our fiducial vector since it's just identical 0. Then when we look slightly more closely, there's actually a way around of that we find that we get a projection permutation action. So we are not only permuting the indices, but we are multiplying by a constant gamma. And the constant gamma, when you look later more closely at it, just comes from the fact that we have a rank 1 projection operator, and therefore the columns are proportional to each other with a fixed proportional constant. And so we can rectify that. Instead of looking at the permutation action on the coordinates of the vector, we look at the permutation action on ratios. For the moment, let's assume that we are just have our first coordinate, which means that the projection operator, the first column is non-zero. So how does the positional work? We still have to compute a numerical fiducial vector, and we now prescribe a particular symmetry. So we pick this symmetry in a way that we have diagonal matrices in the centralizer of that, since the centralizer are the matrices which give rise to our kind of Galois action. This gives a subgroup of the units of our indices, and we can now apply the very same trick that we take the orbit of the coordinates of our fiducial vector with respect to the subgroup, form the polynomials, and we are lifting this polynomial when we have sufficiently high position to make exact ones, calculate exact roots, and by that we have calculated our fiducial vector. The advantage of that method is that we only have on the order of d instead of d squared numbers, and also the field we are working with is a field of smaller degree. So using this method, it turns out that the assumption we made appears to be true for the dimension where we applied that. And we found new exact solutions going up now up to dimension 1299 and a lot of kind of small dimensions. We also have a refinement of the Weyl class field conjecture, since after taking a closer look at the fields we have, there seems to be also a particular Weyl class field in which the solutions live. But for that, you have to wait until I eventually have my paper ready. Let me now finally go to the case when the dimension is a prime dimension, congruent 1 modulo 3. Some might recall that Jean Cobb has looked at dimensions which were congruent 2 mod 3. We are taking just the other case, not divisible by 3. And in that case, Zauner matrix itself is already permutation symmetry. Related to that, the centralizer contains all diagonal matrices, and we have a single orbit under the Galois group. So we can get all our components of our fiducial vector. The first one we normalize to 1 by having the Galois group acting on this one. So what we need, if the order of the symmetry is 3L, we need d minus 1 over 3L different numbers, but they are all the orbit under the Galois group. So what my dream was when I made this observation, I already can conjecture in which field kind of this number V1 lives, but is there any way kind of to determine that number? Is it somehow special? And can we define what are kind of the action on the indices and the action on our element. And it turns out, in collaboration with Markus Grassl, Ingemar Wengson, Michael Harrison, and Gary McConnell, that this particular number is related to Stark units. So I put that up as a conjecture. I'm not completely sure whether my co-authors agree on that, calling it conjecture, but it's something that turns out to work in all the cases, that we can pick the first coordinate. Now it's a strange number, it's no longer 1, but you might briefly see why we picked that number. And the other numbers are square roots of something that looks like a phase factor for physics. So it's a number of modulus 1, complex 1, times the first component and taking the square root of it. The second part, almost flat, just means that the modulus of all of these components is the same apart from the first one. We also can have a conjecture in which field these components lie, and that's a particular Weyl class field where the conductor is effectively a factor of the dimension over this quadratic field, and we have ramification at one place. And what the key part is that the phases we are having here, those are Galois conjugates of so-called Stark units of this particular Weyl class field. I won't really explain what Stark units are, but rather I take the constructive computational approach and ask, what does Stark's conjectures provide us with? So Stark's conjectures tells us that for certain Weyl class field over this real quadratic field, it's not the only case to which Stark makes a conjecture, but that's the case we are looking at. One can compute numerical approximations of so-called Stark units via L functions, which are kind of related to generalizations of Riemann zeta functions. What is more, despite that we have numerical values, Stark's conjectures provide us with a labeling of those by elements of the Galois group. So the Galois group is known by class field theory, and Stark's conjectures provide us with a labeling of them. And then when we have computed the numerical Stark units to sufficiently high precision, using the very same techniques as before, we can get, in first place, the conjectural exact minimal polynomial. It actually turns out that we have a heuristic that allows us to tell what precision is required. When we compute the numerical Stark units just to low precision, just 20, 30 digits, we form the minimal polynomial, and from that we can deduce it. The caveat is that we have to calculate as many Stark units as we have the degree of the field, and in terms of the precision, it looks as if the complexity grows more than cubic. So clearly, we want the precision to be as low as possible. So there are functions in Magma and also in the computer algebra Pari GP from the group in Bordeaux that allow us to compute these L functions, and then eventually we get the Stark units from them. And now when you look here, we have the degree, the logarithmic height, that's the logarithmic height in base 10 of the minimal polynomial numerically. And our heuristic tells us the precision we need is about twice of this height. So we need 1,000 digits precision for dimension 487, and the total CPU time was about 10 days to do that. We can have independent calculations for all of those, which gives us some savings. When we look at the bottom line here, it turns out for dimension 2503, we need a precision conjecturally of 13,000 digits and we have carried out the calculation, it took 60 CPU years. That's really something you don't want to do on your laptop. It will die before that, but that's where we made use of the cluster of the Max Planck Society. And so far, this passed all our checks, but at the end of the day, we still don't have a solution for it. Since in order to get to a solution, and I'm afraid that I'm already running out of time, but maybe I get another 5 minutes for that. So the problem is that in first place, when we look at the number theory picture, here we have the diagram of the fields that are kind of involved. We have our base field, we have the Hilbert class field, and we have this Weyl class field, which is, again, by Stark's conjectures, generated by those Stark units. The way the Stark units are calculated and defined, we get positive real numbers, but then I'm rushing through that. When we have algebraic numbers, there's nothing like positive or negative. Neither is there something like real and complex. It's only when we look at embeddings into the real or complex numbers. And for our base field, the abstract square root of d can either be mapped to a positive real number or a negative real number. So we have two different embeddings. And then when we go to extension fields, we have more embeddings. Essentially, we have as many embeddings as the degree of the field is over the rationals. But also by sloppy notation here, I'm using the same one. And we find that using any embedding above the one, which takes the square root of d to a positive number, the Stark units we have calculated are real numbers. What we are after in the end is actually complex numbers. And those we would get by applying just the other embedding, which give negative numbers. That's also what class field theory tells us, that we are allowed to get complex numbers on that. When we look at the corresponding minimal polynomials, they are the same up to flipping the sign of the square root d in that. When we look at the minimal polynomials over the rationals, those two fields are actually equal. Or say they are not equal, they are isomorphic, they are defined via the same polynomial, but since we don't have a normal extension, so this extension over Q is not Galois, those fields are not identical, and we have to go from one field to the other field. And the computational kind of part obstacle now is we could do everything kind of in the algebraic domain, apply all these automorphisms, but that would require factoring the polynomial as we did before. And we found a way around that. That is by directly going on the numerical level from this one to that one. And that's actually an ideal that is already in the PhD thesis of Jean. That's the so-called Galois polynomial. In the interest of time, I will only highlight what it does. We have that the action on our numerical values, we know kind of how they permuted. And instead of having the algebraic action, we can just define a polynomial that for all the pairs of Stark units, now numerically, mapping them to their conjugates. And what this kind of reduces to is the problem of polynomial interpolation of m points. And what Jean did in his thesis was he phrased that in terms of solving a one-to-one system, which doing it kind of the direct way has cubic complexity. But it turns out that using kind of Newton interpolation, we only need m squared arithmetic operations. One could even do better if one had FFT-based methods, But unfortunately, I haven't seen any implementation for that. So if any of you has one, please let me know. So we are still working with the quadratic one, but that's good enough in our case. Again, we do that on the numerical level. And then this polynomial will have coefficients in the base field. So we can again kind of apply our integer relation algorithm to them and get the exact one. The obstacle here is we don't have a good a priori bound for the precision we need. And it turned out for dimension 19,603, we get coefficients with integers that have 1 million digits. So we need a very high precision to do that. So that's a computational bottleneck. I'm actually skipping that part in the interest of time. The caveat is that we need the square root of our elements instead of the elements. And each of the square roots, or taking the square root, has two possibilities. But it turns out that we can get rid of that and have only one ambiguity in choosing a plus or minus sign in the end. There is another kind of more or less combinatorial obstacle when we have done all of that. And that is the problem that we know that on the indices, we have the unit group of our integers modulo d, which is prime in our case acting, and we have the Galois action of an element sigma. But the problem is we have to identify a correspondence, so we have to test which of the primitive elements does the job. And we have kind of just the two possibilities to choose the sign. And so far, we cannot do better than testing all the possibilities, which are in the end less than d of them. And we compute just one overlap. And it turns out that whenever this overlap has the correct value, then we have a fiducial vector. Of course, this is just a heuristic. So the final problem is, I'm also skipping how to get exact solution, how to verify the solution. It turns out we can make use of our frame potential, which needs cubic many operations. We can do slightly better by looking at these particular terms, which obey some additional kind of both more symmetries. So we can reduce it by a factor of 8. And also we can check each of these terms, whether they have the correct value, instead of only waiting until we have all of that. The big advantage is that the calculations, even for the exact ones, can be done in the small field, since we don't need the D's rule of unity, which would require an additional extension of our field. But the summary now is we have reached dimensions where verifying the solution actually takes longer than computing it. And just to give you some numbers, and also related to what I advertised in the abstract, to verify the solution for dimension 19,603, and for the biggest one, 39,604, we can only make use of the numerics, and using 1,000 or just 100 digits took already several years of CPU time to do the full verification. We have done a full verification for dimension 487 using the exact one. That took 31 days. But we can also have something like a zero knowledge proof by just calculating, checking one of these kind of partial sums. And when we look at dimension 5,709, 5,779, checking just a single of these overlaps takes 1.5 hours, but we would have to check d squared of them. And again, that's effectively out of reach. But we can randomly pick any of the indices, wait 1.5 hours, and we get the correct result. So we are fairly confident that we indeed have solutions, but we don't know whether we have true solutions. So getting kind of to the end, it turns out that the method as I presented it was only applied to prime dimension, but actually we can extend that to all dimension of n squared plus 3. And the dimension 39,604 is clearly not a prime number. But then we have even numbers. It turns out they are divisible by 4, not by 8. And when we can make a chain of bases, we can again work them in terms of flat bases, and we can compute Stark units. Now we have to compute Stark units for more than one field. We get some additional complications, but nonetheless, we have applied the method to 34 dimensions, and we have a lot of 4-digit dimensions and 2 5-digit dimensions, which are clearly beyond what we were able to reach by our numerical methods before. So to summarize, we have a deterministic procedure. Yet, of course, the dimensions we are reaching here are getting so big that deterministic procedures are taking very long. And they are also kind of only partially deterministic in the sense that we don't know a priori which precision we need to compute that Galois polynomial. So that's a bit of an obstacle. As I already said, we didn't find any dimension for which our procedure failed. Big questions now is, can we avoid flipping the sign and just work with the real Stark units, as Jean, Steve, and Markus did with their ghost fiducial vectors? That might also allow us to work with lower precisions, saving the 60 years of CPU time just to calculate the minimal polynomial of the Stark units. There's also the question, can we avoid this combinatorial search in the end, which is getting more complicated when we have composite number, which gives rise to more subfields and more Stark units. And then, of course, the big question is, even if we assume that Stark's conjectures were true, how do we prove that our method works? We have some ideas, but unfortunately, personally, I still feel very far from proving that. And then, since the method applied to dimensions n squared plus 3, only that would still qualify if we are able to prove it in all of them, or just in the prime dimensions, to get the prize money. But of course, we would like to see that extended to all of that. And I hope that, say, at least before the end of year, we'll have our publication ready. There you can get more of the details, and also the details that I skipped now, you can read from the slides. And with that, I would like to thank you, also our funding agencies. And once more, I would like to thank the Max Planck Society for access to computing resources.
All right, let's thank Markus for a great talk.